Good day, class. So the concentration of this last part of the pre-recordings for gas absorption is on the design of the gas absorber or the stripping column. Um, for the design of the column, we have discussed also last meeting. So this is just a review that we are concerned with the size that has something to do with the diameter of the column and the height. Now, for determining the diameter of the column, there's a need for you to know the pressure drop at flooding condition. So when do we say that your column is flooded? So your column is flooded when all of your streams are going to leave the continuous phase outlet. So in this case, if the continuous phase outlet is the gas phase, it's going to leave the top of the column. That is referring to both your gas phase and your liquid phase. So both of them will leave the top of the column. So your liquid phase, which is supposed to leave the bottom of your column, carrying with it the solute that is taken out from the gas phase, will now leave the top of the column. And in that scenario, we say, or in that particular condition, we say that your column is flooded. So there's a corresponding pressure drop for that condition, and we determine it based on the packing factor. Now, this packing factor, this packing factor is taken from a property table, and it's based upon the packing material that is being used by your pack column. So we know that for packing materials, you can either have structured packing materials or random packing materials. So we take it from a particular table. I will show to you in a little while this same table, which was also discussed with you last meeting. So these are the steps that you need to do in determining the size of your column, which is based on the flooding condition. So first, you determine the packing factor, which you will be using in the formula that was shown to you in the previous slide to determine the pressure drop when the column is flooded. So take note of the unit. It's inch water per foot of packing material. And this is the corresponding formula for that. Okay, this is the formula. Now, a typical flooding velocity is 6.6 feet per second. So your column is flooded already at this condition, or we say 2 meters per second. So even beyond this, or more so beyond this value, your column is very flooded already. So once you know already the linear velocity at flooding condition, you will use it together with the volumetric flow rate of your continuous phase. The continuous phase is the feed. So in the case of gas absorption, your feed is the gas phase. So in the case of stripping, your feed is the liquid phase. So the volumetric flow rate of that, you're going to divide by the linear velocity to give you the cross-sectional area of your column. Of course, if you know the cross-sectional area of your column, it's so easy to determine already its size or its diameter. So this is how we determine the size of the column based on the flooding velocity. Now, this is the table, a snippet from John Copley's of the table we're going to get the packing factor. So this is the column which contains the packing factor. So you have two sets of columns here, one that uses per foot as the unit, the other one is per meter. Okay, you will use that in your determination for the pressure drop. Now, for you to be able to know the very important linear velocity when your column is said to be flooded, you need first to determine the flow parameter. And you can see here that your flow parameter needs the molar flow rate ratio of the liquid in the gas phases and their densities. So you need to get the density of your liquid and vapor phases. This GL over GG can be taken from the given information in the problem because this has something to do with the flow rates. Now, once you have the flow parameter computed, you use it here so that you can locate the particular x coordinate that should go with the delta P. These curves here, the curves that you are seeing here as an example, this one, are the delta P curves. So the delta P that you have determined, or the pressure drop together with the flow parameter, will lead you to the capacity parameter. Now, using the densities again of the vapor and the liquid phases, together with the packing factor and the kinematic viscosity V here, you'll be able to determine the linear velocity. And of course, after that, you will be able to determine the cross-sectional area, then eventually the size of your column or the diameter of the column. Now, for this particular figure, we have the pressure drop correlation of random packing materials. We have a different correlation for structured packing materials. So be very careful with what particular pressure drop correlation diagram you're using, because we have two. One for structured packing and one for random packing material. Now, if our column is not a packed column but rather a tray column, we need the tray factor, K sub B, in here in the first step, and it should be taken as well from a figure, which I'm going to show to you in a little while. And using this particular tray factor together with the interfacial tension depending on the liquid or on the system that you have. So the interfacial tension for organic liquids is 29 per centimeter. If it's water, it's 72 dyne per centimeter. Now, you substitute that interfacial tension values here together with the densities again of the liquid and the gas phases. And of course, that tray factor which you're going to get from a figure or from a diagram. You'll be able to determine the linear velocity when your tray tower is flooded. Typical value starts at 3 meters per second onwards. So at 3 meters per second, your column is already flooded. Now, by the way, what would be the corresponding linear velocity that you will use? That way your column will not be flooded, because the velocity that you'll be getting here, in step 2, is actually the condition when your column is flooded already. So we use 70% of the computed linear velocity here, and that particular 70% will be the one that we're going to use together with the volumetric flow rate of the continuous phase, and that's your feed phase. Okay, the same principle, the same procedure we will do in the case of determining the size of a packed tower. So a while ago, I have shown to you the figure for determining the diagram for determining the linear velocity at flooding. So this is already a condition when your column is flooded after you have taken the capacity parameter. So what are you going to do with the computed V sub G? We're going to use the value that is suggested by John Cooklis, the value or the percentage value of the computed maximum linear velocity in determining the size of the column. So whatever is the V sub G that you got here, you multiply it only to 60%. 60% of the computed linear velocity will be the velocity that you will use together with the volumetric flow rate of the continuous phase to be able to determine the size of your column. Okay? So for packed column, it's 60% of the computed maximum linear velocity. For tray column, it's 70% of the computed maximum linear velocity. Okay? So that's in the case of determining the diameter of our tower or our column, whether we are talking about gas absorption or stripping processes. Now, this is the figure, or this is the diagram where you are to get the tray factor, K sub B. You'll be needing here the ratio of the liquid and the gas phases, and of course their densities again. Now, the plate spacing, which is represented here by these different curves, should be specified in the problem. So you need the tray spacing together with the pre-calculated value to get the tray factor. and then just substitute the value of the tray factor to the formula that was shown to you for the tray tower. Okay? Now, these are problems that you'll be able to read from John Cookleys that illustrates the use of the formulas and the steps outlined in these slides in determining the diameter of your column, whether you are given a pack tower or a tray tower. So this sample problem 10.6-1 in pages 661 to 662 is an application of determining the size of a packed tower. Whereas sample problem 11.5-2 on pages 730 to 731 illustrates the use of the tray factor in determining the size of a tray tower. Now, sample problems 10.6-4 to 10.6-5, so there are two in here on pages 672 to 679, are sample problems regarding the determination of the tower height. Okay, so there are actually three different methods that you can choose from in determining the tower height. And I will illustrate it with a simple sample problem in a little while, and you can add these two sample problems to those to that particular problem, which I think I have prepared 5 different procedures in determining the tower height. Now, all of these sample problems are taken from Principles of Transport Processes and Separation Processes by Gian Cookleys, the Philippine edition, that is the most recent edition. So please look this up. That way you will have also a guide on how you're going to tackle problems concerning the design of the tower, specifically the height and the diameter. Now, when we speak of the height of the tower, so we can use the number of, shall I say, transfer units. This method uses the number of transfer units. The equation can be found in your handbook. It's indicated here, equation 14-15. So meaning it's taken from section 14 of your handbook. So you can have for the Z, the height of your pack tower, these 4 different formulas all will have comparable values on the height. So it could be HG and G, HL and L, or the H sub OG, N sub OG, or the hognog, H sub OL times N sub OL, or the hull null. So the subscript G means that in determining the tower height, you have used the gas phase resistances. You have considered the gas phase resistance. This is in the case when the problem is gas absorption. If the problem is stripping, you are to use the H sub L, N sub L. Okay, so here, this time you are basing the determination of the tower height on the liquid resistance. Okay, so anyway, if it's H sub OG, N sub OG, so on the original subscript G and L only, you have added O. So if you have already O in your subscript, that represents the overall, let's say in the case of G, the overall gas phase transfer units. Or if it's H sub OG, it's the height of one transfer unit based on the overall gas phase transfer unit. So if you have already the O, meaning it's the overall gas phase resistance that we are considering. Okay, if it's OL, it's the overall liquid phase resistance that we are considering. We use the HG hognog for gas absorption. We use HL hull null for stripping. For the N, it's referring to the number of transfer units depending on the specified subscript. So if it's G, it's referring to the gas phase. If it's L, the liquid phase. For HG, it's the height of one transfer unit based upon the gas phase resistance. H sub OG, as I've mentioned a while ago, is the height of one transfer unit based on the overall gas phase resistance. So you already have overall there because you have together with the G, the O. So if it's H of OL, it's the height of one transfer unit based on the overall liquid phase resistance. Okay? So we consider the liquid phase resistance if the problem is tripping. We consider the gas phase resistance if the problem is gas absorption. And this particular set of formulas uses what we call as the number of transfer units. Okay? Now, your NOG-NOL has an equivalent formula also in Jan-Kuplis, and this formula is this time are functions of your slope for the equilibrium line, the gas absorption factor A, and the mole fraction. So you have Y1, Y2, X1, X2. Now, as for formulas that you could use found in your handbook, I have written it here. So please check on these formulas as well. Okay? Regarding the null, nog, hol, hog formula. Now, we can also compute the Z. So that was the first method. You use the number of transfer units formula. You can also determine the Z using the film or overall mass transfer coefficient. So if it's just the film transfer coefficient, it's just small k sub y prime A, or it could be k sub x prime A. If it's just the film mass transfer coefficient. If it's the overall, in this case here, you have overall mass transfer coefficient. The two K's that are written here as small letters will now be written as capital letters. So you will have, write it here. So you will have here, K sub y prime A or K sub x prime A. So it's now capital if it's overall mass transfer coefficient. Now, for dilute solutions, oftentimes our solutions, the solutions that we need to process are dilute, meaning the concentration is 10% or less than 10%. So these are the equations that are given in Jan-Kuplis for you to determine the tower height based on the film or overall mass transfer coefficient. Now, Jan-Kuplis also has its set of formulas using the transfer unit. So the two sets of formulas are those formulas for the concentrated solutions, meaning the concentration of the feed is higher than 10%, and those that are considered dilute. So if it's dilute, then that would mean that your solution has a concentration of less than 10%. Now, another method that we could use is the method utilizing the height of packing equivalent to one theoretical stage, or that's the HETP. This is for pack towers as well. So you can determine the HETP using the hog. So first determine the hog and then use the gas absorption factor together with the hog to determine the HETP. Then you will have the nog here. You can determine the nog based on the number of transfer units. This number of, not number of transfer units, but the theoretical number of stages. N here, capital N, is the theoretical number of stages. Again, multiplied with the ln of A divided by the quantity 1 minus 1 over A. So your nog here is based on the predetermined theoretical number of stages N. Okay? Your hog, your HETP rather, is based on the hog. The hog maybe that is given in the problem, or the hog that you also predetermined based on the formulas that were given in the previous slide. But nonetheless, these two formulas are found in your handbook and the equations are indicated here. So how do we use the HETP in determining the height? Z. That would be HETP multiplied to the theoretical number of stages. Though this particular set of formulas relating HETP to HAG and NAG to N, these formulas are applicable only for systems in which your packed or tray tower has what we call parallel operating line and equilibrium lines. If the operating lines and equilibrium lines are not parallel, then you cannot use these formulas here in determining HETP based on HAG and in determining NOG based on the theoretical number of stages. Okay, so this is only applicable for operating lines and equilibrium lines that are said to be parallel. But in the sample problem that I'll be giving you in a little while, one of the procedure there use this particular set of formulas, and you can see the degree of variation of the answer, or the let's say the difference of the answer using this particular set of formulas with the formulas that are supposed to be really used for the set problem. Okay, now so this is the problem. Acetone is being absorbed by water in a packed tower having a cross-sectional area of 0.213 square meter at 293 Kelvin and 180 M. The inlet air contains 2.5 mole percent acetone and the outlet 0.3%. So this is a dilute system because the inlet air contains only 2.5 mole percent acetone. So it's less than 10%. The outlet is 0.3%. The gas flow is 11.43 kilogram mole inert air per hour. So take note that this is already, let's see here, 11.43 inert air. So meaning the gas flow that is indicated here is not the total gas flow. This is just based on the air present. So your solvent, on the other hand, is pure water, and the value is 55.08 kilogram mole water per hour. And we're given here the film coefficients K sub y prime A and K sub x prime A. Now, equilibrium data for this system shows that when the mole fraction of acetone in the liquid phase is 0.0333, the partial pressure of acetone in the gas phase is 30 millimeters of mercury. What is the tower height? Actually, you could see already that letter C here is highlighted. Actually, this is the height of our column. It's 1.36 meters. Now, as to the procedure that I'm going to show to you on how to find this value, there are 5 different procedures, all of which have their advantage over the other. But of course, you have to take note that this is gas absorption. So whether we use the number of transfer unit procedure or the film coefficient or the mass transfer coefficient procedure or the HETP procedure, there will always be variation if we're not going to base our computation on the gas phase resistance. In this case, it has to be based on the gas phase resistance because this is a gas absorption problem. Okay, now let me just share to you the it's here, the solution for this problem. Okay,